All right, our last speaker of this session is Neil, who, if you remember his talk from last time, is now an IEEE magazine. I've forgotten which magazine.
Computing in Science and Engineering.
Yeah, it's an article in that magazine, so check it out.
Yeah, on floating point accuracy. So this is something completely different, though parts of it inside are a little bit related. All right, so in the last couple of months, I've been in my man cave making something, doing a 3D engine. Now I have to explain what a 3D engine is. It's a high-level abstraction layer. It's usually a library between your program and a GPU that sort of looks like this usually. You have a program that outputs things to the 3D engine, which talks to OpenGL or Direct3D, which knows how to talk to your graphics card. So it's like a three-step process. The reason you'd want a 3D engine is because talking directly to OpenGL or Direct3D is painful. You want to talk in a high level about, spaceships and things, and not specifically about vertex shaders and stuff like that. Examples of things like this are Unity, Unreal, Rage, or at least the 3D rendering parts of these engines, not the networking and all the other stuff that they do. The problem with all of these, though, that they're all built around mutation. So I wanted to do a purely functional 3D engine. Thought that would be pretty cool. Now, I could talk for about 1,000 words on on what a 3D engine does, but I think a picture does better. Now, if you saw that baby head and you immediately thought, hey, that's the floating baby head from Phineas and Ferb, then I salute you as one who is cultured and awesome. If you didn't know who that was, then yeah, you should watch Phineas and Ferb. The funny thing, my 7-year-old daughter, when she first saw that, she laughed. She's like, you put a body on her. Yeah. So anyway, so this picture is 100% not creepy. And yeah, so this is what the 3D engine does. Right. It spoon feeds a giant baby. The giant baby, OpenGL, which is connected to the graphics card, it consumes homogeneous, bland, first-order vertex data, and instead of rocket ships and cars and things, you often have to trick the giant baby into eating things. For example, I had a very difficult time getting my giant baby to eat 200 matrices per frame, and so I mixed them in with the vertex data, and that worked out okay. The giant baby is very hungry, but can only swallow a few hundred spoonfuls per frame. That's all you get. So, to give you an idea of how hungry this giant baby is, a typical AGP bus will accept, 2 gigabytes per second of data. It'll shuttle that amount to the graphics card, which ends up about 35 megabytes per frame at 60 frames per second. Very hungry, but you only get like a few hundred spoonfuls. So the engine manages that for you. Most engines have an API that's very imperative. You give commands. Add this shape, move this shape, load this map, put this light here, transform this thing, put the gun on the attachment point of the thing, and then draw the scene. And internally, the 3D engine keeps a scene database, which keeps track of all the things that it's going to be showing. It's also got algorithms like frustum culling and some basic collision detection, and of course the high-powered blender by which you make the bland vertex data that you send to the giant baby head. Now, the scene database inside of an engine, it's just a data structure that makes spatial queries efficient. For example, a point inside query. Is this point inside of something, and if so, what? So let's say that I give my engine a command to add a sphere, because as we all know, a sphere is a great first-order approximation to pretty much any shape in the world. So you put one inside the engine, and one of the first things the engine will probably do is put a bounding box on it. The reason is a point inside query is very efficient against a bounding box. It's just 6 compares. Against a sphere, it's more. So it puts a bounding box. I didn't want to calculate. It's like 12 floating point operations or something. So it puts this bounding box on it and then puts it inside the database. And then you say, add another sphere. So the engine will put another bounding box around that thing. Now, what it could do is keep a big list of shapes with bounding boxes, and then when you do a point inside query, check it against each one of them. But that would be kind of slow. So what it does instead is put a bounding box around both of them and keep this big bounding hierarchy. If the point is not inside of that bounding box. That implies it's not inside either of the other two bounding boxes, which implies that it's not inside either of the two spheres. It tends to turn most queries into order log n things that would normally be order n. Now, most databases are bounding hierarchies like this, and they're mostly structured like trees. And if you're a functional programmer, as soon as you see the word tree, you're like, ha, ha, ha. I wonder if we can make that purely functional. And indeed you can. It's actually very straightforward. So here's what I did. Take the tree, or the scene database, out of the 3D engine and make it something you can actually manipulate instead of giving commands to the engine. You make a shape, make a light, which makes scenes. You can take the union of a couple of scenes, which puts the two scenes together, do some transformations, and unfortunately there's one imperative thing left. Draw the scene, which is basically like a printf, so it's not that imperative, it's imperative. Anyway, so, and that will put everything in the high-powered blender and send it to the giant baby. So, awesome, let's try it. At our Dr. Racket REPL, we type in, define my unit sphere. Take this shape, make a scene. This sphere happens to be, well, you can totally tell from the numbers, but it's white and it has a green glow. Yeah, that's annoying, isn't it? And then I'll take this unit sphere, and this is pretty cool. I'll make a union with it with a transformed version of another unit sphere, and because we're entirely stateless, we can reuse this unit sphere, which is nice. We'll just move it one unit in the x direction and take the union. And then Dr. Racket's REPL spits out this, which is obviously two giant glowy spheres right next to each other. Okay. No, what? Yeah, oh, yeah, it's lovely. We can do better than that. Here's a more excellent way. So on top, or a wrapper, I've also been making a wrapper around the 3D engine. I'm calling it Pix3D. So you require Pix3D, and you can write something like this with an emitted color of, see, that's red, green, blue, red 0, green 1, blue 0, and it's 2, which is its intensity. It's kind of glowy. Combine these two spheres. One says one place and one's in the other place, and you get that at the Dr. Racket REPL. This is actually still not very satisfying because it's only one projection of these. We have no idea what this looks like from behind, for example. So I can show you here. To combine the sphere. Wow, that was my trackpad. So our unit sphere at the origin, and then one that shifted a little to the left, and now we have, the first time it draws, it always takes a bit. There's initialization work. If I click on it, then we can use WASD and the mouse and move around the picture, and that's what it looks like from behind. Okay. Thank you. Thank you. Oh, they clapped for me. Okay. So obviously we can't just do spheres. We should be able to do things like rectangles. So I put in 2 endpoints and we get a rectangle. This will show us something we couldn't see before, and that's the coordinate axes for the shape. So there's our rectangle sitting right there with its corner at 0, 0, 0. And so we don't have to keep on typing that. We'll define it. Unit rect, we'll call it unit rect. I also want a chocolate rect because I like chocolate with color chocolate. And we'll just take, I don't have to copy that. All right. Cool. So I have my unit rect and my chocolate rect. Oh, if I spell it right, I have a chocolate rect. And oh, that's right. I do have to copy it. It doesn't work like Pix. It doesn't actually, it doesn't recolor things that don't have colors assigned. I'm still trying to work out the best interface for that. So now I have a chocolate rect. If I want, I can put the two things together using combine. I combine the unit rect with the moved chocolate rect. I'll move it 1 unit to the right. And I might want to do something like rotate it around the y-axis, -30 degrees or something like that. And we got a little Z fighting, but there it is. It's been rotated. Now, what if I wanted to put the chocolate rectangle, if I wanted to stick the base of it, like right in the corner of the other rectangle? It seems like using these kind of operators would be really, really difficult. And yeah, it would be. So I've added these things called bases. They're kind of like pinholes if you've used 2HTTP image You've seen these before. So a basis. I'll set a basis. They're always named. Unit rect. I'll call it the corner basis. Let's see, normal basis. I'll put it on the corner. That's the coordinate of the corner. And this is the direction that the z-axis points. There. Now I have a rectangle with a basis. Now these kind of act like attachment points. If you used modeling software before, you've known what attachment point is. It's just a place you can stick things. So I'm going to do that to the chocolate rect as well, except I'll put it right at the base of it. Let's see. It needs different coordinates. 1/2, 1/2, 0, and I'll have it point straight up. So now I have a basis sitting on the bottom of it. And when I have these two things, I can pin them together.
What is two?
Hmm?
Oh, you have two coordinates because one just comes built in. Yeah.
Okay, thanks, Jay.
We saw two XYZ axes.
Oh, yeah. One of them is the coordinate axes. These are bases. They look the same for a good reason, and that's because they're basically the same kind of thing. And I will, I named this corner. I want to call this base instead. So I'll pin the corner to the base, and now I have the chocolate rectangle pinned to the corner of the other rectangle. You can use this to make things like, animations in like this one. In a flight sim demo that I'm working on, I'm using it for figuring out where to put the blaster bolts when you fire things from your ship. I am still working on exactly what the right combination of combinators are for this to create scenes and things. Now you might be wondering if this is fast. And this is fast because I begged Jay to tell me what his secrets are. Well, not really. We're just in a chat room. He's like, you shouldn't do it this way. You should do it this way, which So this is 70,000 spheres and 500 lights running at 60 frames per second. Racket is sending that amount of data to the graphics card every frame. Thank you. Now, one thing that makes this extra cool is that these spheres aren't composed of polygons. They're not discretized. They're actually ray traced on the card. So 70,000 ray trace spheres on the card. Yeah. Okay, so those were the demos. All right, I had some design goals going in. Make it fast was one of them. It might require users to tweak things or to give hints, say like, I use this shape a lot, do some pre-compilation so you can, put it in the scene really fast or send it to the graphics card quickly or even upload it to the graphics card right now so I can call it anytime I want to. This makes the high-powered blender inside the engine unsafe and impure and pretty evil and ugly looking, but anybody who uses Pic3D or even the engine without the Pic3D wrapper doesn't ever have to see that. From the outside, it looks entirely stateless. Another one of my design goals was to use and allow modern rendering techniques. So in other words, to make it cool. Sorry, Jay. I don't know. Retro is cool too. It's coming back in. But I'll talk about what some of the modern rendering techniques are in a bit. This is my main one, though. Minimize confusing surprises. I'm going to be using this, or at least I'm going to be I'm going to be using my kids as guinea pigs and teaching them computer science and mathematics using this 3D library. And I don't want my son running into something and not being able to do something, and I give him some just stupid explanation that makes sense to me that doesn't make any sense to him. The other thing, this is very interesting. Using modern rendering techniques and minimizing confusing surprises often go together. I'll give 2 examples of that. All right, I want to talk about one of the dumbest decisions ever made in making OpenGL. The depth buffer. Actually, the depth buffer is very cool, but how they implement it is not. Who knows what a depth buffer is? You've done 3D, so I've got... Wow. Okay, so... All right, whenever the graphics card writes a fragment of a shape, you'd usually call it a pixel, but it writes a fragment of a shape onto the screen. It also writes in a separate buffer, invisible, how far away it is. And then if it ever writes another fragment in exactly the same place, it also figures out how far away it is. And if it's farther than the thing it already wrote, it just doesn't draw it at all. That's how you can have things like intersecting spheres and stuff, and they all look consistent. Now, there has to be then a function from distance to the values that you can put into the depth buffer, and this is the default one for when the nearest thing you can see is 0.1 units away and the farthest thing you can see is 10 units away. And if you'll notice, the maximum precision is here, and if we're thinking meters, it's like about right here. 0.2 meters in front of your face is where the maximum precision is. And then as you get toward 10, let's see, it gets really close to 1. Now, in floating point, the floating point numbers are really, really dense around 0 and extremely sparse away from it. So as the value that gets written to the depth buffer approaches 1, you get just error all over the place. And I'm going to demonstrate that. So here's an example of a confusing surprise that happens because of OpenGL's stupid way of using the depth buffer. So I have two groups of 3 spheres. One's a ½ meter away and one's 16 meters away. And the one that's 16 meters away is bigger, so they look about the same size. Okay, now look at the seams between the spheres. So I'm going to double this distance and also double the size. So it got a little bit more jagged. At 64 meters, you can really see the jaggies now. And at 128 meters, 256, this is just... I'm sorry, Joseph, you can't draw anything that's more than 4,000 meters away because it looks bad. We can't have that. So, fortunately, some other people have come up with a nice way of doing this and come up with a different function, a way of overriding what OpenGL does. It's called a logarithmic depth values, and you get constant precision everywhere. And the upshot of this is everything from 1 millimeter to 2 million meters away is perfectly consistent with this kind of depth buffer. So minimize the confusing surprises. Now, another kind of confusing surprise you might have is, well, let's say you're writing an engine and you want to light things. So you draw some shapes on the screen, and you have to calculate from every light which one's influencing the amount of illumination that's being reflected from the shape at every point on the shape. That's order m times n in the number of shapes and lights, which is really kind of slow. A modern rendering technique gets around it. It's called deferred lighting. So you end up drawing things in multiple passes. The first pass, you don't actually draw the shapes. You draw their normals. You draw, excuse me, the vectors that are perpendicular to the tangent lines on the surface, or the tangent plane on the surface. Then in the next pass, you draw just the lights. None of the shapes. You draw the lights and figure out what they're illuminating. And this is really cool because it only draws on the things that are actually on the screen instead of stuff that you will never see. And then you do another pass where you draw the colors. You draw the shapes again. Using the information from the last pass, you can give them the proper colors. And then, of course, because we want to be cool and modern, we do some extract, overbrighten, blur. We do some, HDR rendering. And finally, we combine everything and tone map it to produce the final image. This is order m plus n in the number of shapes and lights, which means that if you want to scatter lights across your entire scene just to, to make it really cool and moody, that's perfectly okay. No confusing surprises. But the best way to minimize confusing surprises is, well, it's purely functional, right? You never have to worry about the state of the engine or the state of the scene because they're stateless. There's some pretty cool advantage to this. Printf debugging is crazy useful this way. If you notice something weird going on in your game, you can add a little hook to, you press the spacebar and take a screenshot, which basically means print the screen to the REPL, and then you can fly around inside it and look. See what happened. Store scenes or rewind a game to record a demo. Very cool things. So, now what? I want to make this work on all 3 major platforms. I know it does not work on Mac OS X because of reasons. And I can only develop in OpenGL 3.0, and in Mac OS X you only get OpenGL 2.1 or 3.2 or 3.3. And 3.2 and 3.3 aren't backward compatible. I don't know how it does on Windows, so if somebody wants to try this on Windows, please do it. I want to make this work in untyped Racket because it doesn't work in untyped Racket right now for reasons. That have to do with contract generation, and Asuma's like back there because he knows why. Let's see. I have a picked 3D canvas. I'd like to do game canvases which keep track of which buttons you're holding down and things like that. And I'm very close to making a Big Bang 3D, or actually, since now I've seen Jay's talk, I want to try it his way. That looks very cool. Other shapes and shape combinators. Right now I have triangles, spheres, and rectangles. I have no textures because I don't know of a good way of I don't know of a good human interface for putting textures on things in a procedural way. I'd also like to make it so you can run your own programs on the GPU. So instead of ray tracing a sphere, you could ray trace whatever you like. Other modern techniques, and Cairo rendering. Initially, I did this because I wanted to factor out the 3D engine from plot so I could test it on its own, and then it sort of turned into something else. I want to go back to that. And of course, faster, 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 faster. I always want to make it go faster. That's me. You? Let Pict3D spoon feed the giant baby for you. You can install it today. Reco package, install Pict3D if you're brave. Thanks.
The advanced rendering techniques that you're talking about, are those things where you're doing things in the engine that are tricking the graphics card into doing things that it doesn't normally do, or are those just...
Sometimes. Yeah, sometimes. Actually, an awful lot of those come down to that. Well, here's an example of an advanced rendering technique. To do shadows, you render a scene from the point of view of the light source. So you re-render everything. Actually, not everything. You call out everything that the light would never illuminate, and then do that. So it's kind of like tricking the graphics card. But it's just smart things other people have come up with to make things more photorealistic and performant, and less surprising very often. Yeah.
Port Quake 3 Arena.
That is a good idea.
The source code is available. All the game data is available.
I used to do a lot of Quake 3 Arena modding years and years ago, and I'd be very... Yes, I should probably do that. That would be fun.
So, now this is my freshman course?
In your freshman course right now? Not right now. Eventually.
When?
Oh, when?
February. January?
Yeah, January.
On, man. Thank you.
All right, we'll start the next session at 3:05, and let's thank Neil one more time.